Today we are here to discuss the topic refractive index. Before going into refractive index, I'd like to mention about refraction. The light bends when it travels from one medium to another medium due to the change in the velocity, change in the speed. So here I is the angle of incidence and R is the angle of refraction. Now this gives you or defines you refractive index according to the Snell's law of refraction, that is the ratio of sine of angle of incidence to sine of angle of refraction is a constant and is given by the letter mu, which is called the refractive index and is a constant. Mu is a dimensionless quantity. So this mu can also be written as mu21, which is the refractive index of the second medium with respect to the refractive index of the first medium. So you can also write refractive index of the second medium with respect to the first medium in terms of velocities, which is velocity of the light in the first medium to the velocity of the light in the second medium. Now here I would like to define absolute refractive index, which is nothing but the ratio of velocity of light in vacuum to velocity of light in medium. So which can be written as C by V. Absolute refractive index is generally represented by mu. Otherwise, if it's a pair, you can write it as mu21. Now C, as we all know, is nothing but a product of frequency and wavelength, nu lambda. So here it is nu lambda vacuum by nu lambda medium. But nu does not change when it travels from one medium to another. So this remains the same and it can be cancelled. So you get another formula for absolute refractive index, which is lambda of vacuum by lambda of medium. So this can also be written as refractive index of the second medium to the first, if it is a case of pairs, as lambda 1 by lambda 2. So now here we are able to set a set of formulas for the refractive index. It says refractive index of the second medium with respect to first is sin I by sin R. It is mu2 by mu1. It is v1 by v2. It is lambda 1 by lambda 2. You can see that the refractive index is inversely proportional to the velocities. So this idea of refractive index helps us to solve numericals as well as gives you an idea whether light would bend towards normal or away from the normal, provided we know two cases. In case 1, if we know when light travels from one medium to another medium, if the velocity of the light in medium 1, that is v1, is greater than v2, or the other information where sine of angle of incidence is greater than sine of angle of refraction, since angle of incidence being too small, you can write it as I greater than R, then we are very much sure that the ray would bend towards normal. Let's go for the other case when the light travels from one medium to another medium, that is from medium 1 to medium 2, and if the velocity of the light in medium 1 is less than the velocity of light in medium 2, or take the other case where sin I is less than sin R, similarly I is less than R, then the ray would bend away from normal. So it is either the case, if we have this idea, you can say that the ray bends towards the normal, or if you say that the ray bends towards the normal, you can draw to the conclusion the velocity of light in the first medium is greater than the velocity of light in the second medium. Moving on to the next one, that is principle of reversibility of the light ray. Principle of reversibility of light ray. When light ray undergoes refraction or when it travels from one medium to another medium, like how, as is the case, we can see that is a rarer to a denser medium. Here it bends towards the normal. The light ray can also go from denser to the rarer medium along the same path. So now here, if light travels from first medium to second medium, you can write refractive index of the second medium with respect to first as mu2 by mu1, which is the case of sin I by sin R. Now, if the light ray is traveling from denser to rarer medium, you can write it as refractive index of the first medium with respect to second. It can be mu1 by mu2, and here it can be sin R by sin I. So now, in order to find further, if I take the product of the two refractive index, sin I, instead of refractive index of second medium with respect to the first one, sin I by sin R, refractive index of the first medium with respect to the second one, into sin R by sin I, which we get it as 1. So this arises you to another formula of refractive index. That is, when we know refractive index of the first medium with respect to the second, or second medium with respect to the first, we can find either one. Like if I know the refractive index of the second medium with respect to the first one, or the first one with respect to the second, I can easily take the reciprocal. So this is the refractive index of the second medium with respect to the first one, provided I know the refractive index of the first medium with respect to the second one. So this refractive index also helps us to give applications. Let us see two applications. Application 1 is the one that is, what is the height at which an object is raised due to refraction? Let us take the example of a coin in a beaker containing water. Now, if the object is positioned at point O, and if the light ray goes from a denser to a rarer medium, the light ray would bend away from the normal due to refraction. And here you can see angle of incidence and angle of refraction. But our eye is used to seeing things straight, so you would see the image of the object somewhere here. Let us mark it as I. And if T is the thickness of, or the depth at which you have the water level, and A is the air and W is the water, then we get the refractive index of air with respect to water as sin I by sin R. But using principle of reversibility, we can get the refractive index of air with respect to water when we know the refractive index of water with respect to air. So this can also be written as real depth by apparent depth. So here we know another way of representing refractive index, which is real depth by apparent. Now here real depth is nothing but your AO. This is the actual depth. So we write it as AO, and the apparent, that is which we appear to see, which is AI, which is shallow one, it's AI. Now this gives you also the apparent depth formula, which is AO by mu. Here in general we are writing it as mu. So if we want to find at which height the object is raised, this can be written as AO minus AI. Now we know what is AI. AI is AO by mu. AO minus AO by mu. Since AO is T, we can arise at T minus T by mu, which would give you T as common 1 by 1 minus. So this would give you the depth at which, or the height at which the object is raised. Moving on to the next one, which is again the application of refraction, that is total internal reflection, which is the case of refraction. That is, when light ray travels from a denser to a rarer medium, as we all know, light ray would bend away from the normal. Now, as you keep on increasing the angle of incidence, at a particular angle of incidence, the ray would no longer bend away, but it would travel parallel to the plane. Then if you increase it further, it would totally come back to the same medium, and this phenomenon is called total internal reflection. Now, the angle at which the sine of angle of refraction is 90 is called as the critical angle, and this helps you again to define or give an other form of refractive index, or the other formula for refractive index, which is given as the following. If I take this as the first medium and this as the second medium, because light is going to travel from denser to the rarer. So refractive index of the first medium with respect to the second can be given as sin IC, and this becomes your R by sin R. Now this sin IC, now since the R is 90, you can write it as sin 90, and sin 90 is 1. But we all know refractive index of the first medium to the second medium is of reversibility, second medium to the first one. So now we shall equate it, refractive index of the second medium with the first as sin IC. Or I can write this as refractive index of the second medium with respect to the first as 1 over sine of angle of critical angle. This gives you another formula for refractive index.